Hi, let's talk about transformers, how our electrical grid works, and the whole reason why we really opted for AC rather than DC during the generator wars in the latter part of the 19th century. So, the biggest advantage with AC over DC is you can use transformers. And with transformers, you can transform voltage at the expense of current. So say we have a power supply that is putting out a total power of 500 megawatts, and the generators are operating at 25 kilovolts. Well, that means the current being produced would be our power divided by our voltage, so 500 mega divided by 0.025 megavolts would give me a current of 20,000 amps. Now, with a transformer, the first transformer rule says the ratio of voltage per number of turns on each side of a transformer is constant. So V1 over N1, input voltage over input number of turns, equals V2 over N2, output voltage over output number of turns. So say we want to distribute that electrical energy at 750 kilovolts. That means we need a step-up transformer where we have more turns after the transformer than we have going into the transformer. And the number of turns on our output would be the number of turns on the input times the output voltage over the input voltage. So 750 kilovolts divided by 25 kilovolts gives me a factor of 30. So if this transformer has 5,000 turns on the input, it's going to have 150,000 turns on the output. Now later on, as it gets closer to the consumer, you want to step it down to lower voltages, which are much safer, so you then have a series of step-down transformers gradually lowering it to the household voltage of 120 volts that we use in the United States. Now, the trade-off is as voltage goes up, current has to go down because energy has to be conserved. We can never get more power out of a transformer than we put into a transformer. So the voltage times the current would have to be constant. So if the voltage over the number of turns is a constant in a transformer, the number of turns times the current is also a constant. So our output current would be our input current times our input number of turns divided by our output number of turns. So that means that if our voltage goes up by a factor of 30, our current goes down by a factor of 30. And 20,000 amps divided by 30 means I'd have 667 amps going through the transmission line. 20,000 amps, 667 amps, both sound like really, really large currents, and they are. But the reason why we do this is because of the energy that would be lost in transmission. The electrical grid has resistance. So say the effective resistance of our distribution line is 8 ohms. Well, if we're trying to supply a constant current through that 8 ohm resistor, the power that we lose to that resistor is our current squared times our resistance. Well, at 20 kiloamps, 2 times 10 to the 4 squared times 8 ohms gives me 3.2 times 10 to the 9 watts, 3.2 gigawatts, which is almost 7 times more power than our power supply is able to produce. Which means if we just tried to transmit everything at 25 kilovolts, we would lose all of the energy along the way because we usually don't build power plants right next to where we're actually using that power. So, solutions include trying to lower resistance, which is something that we really do try to do and should be making a more concerted effort of doing as we work on hopefully modifying our electrical grid. But we can also use transformers to step up to higher voltages, because at higher voltages, lower current means less energy loss. So at 667 amps, the power that we would lose would be 30 squared times smaller, or 900 times less. So instead of 3.2 gigawatts, we'd lose 3.6 megawatts, which would be about 0.7%. And if any electrical company could actually achieve that level of loss in the grid, they would be ecstatic, because that's small compared to what actually happens. Thanks for watching.